Okay, guys, let's go ahead and talk about this warm-up, and then we can get into our notes today, introducing magnetism. You will have a homework assignment that you can start in class, but you may end up needing to finish it at home, and that is 1202.1 Magnetism Basics Problem Set. So let's take a look at the warm-up. The first question says, what causes some materials to be magnetic? And the second question says, what do you think would happen if you placed the north pole of one magnet next to the north pole of a second magnet? Does anybody have any thoughts on what causes materials to be magnetic?
Electric charges.
Electric charges. Yep, you should have that in there. Specifically, moving electric charges would be a good thing for you to add in there. That is actually the cause of magnetism, and we are going to talk about that a little bit more today. And then the second one, anybody have any thoughts? Y'all should know this one. I'm sure you've played with magnets before, but what happens if you put the north pole of one magnet next to the north pole of another magnet? They repel each other. Like poles will repel, opposite poles will attract. Yes.
What separates like the north and south? Like, is there anything different going on in the magnet? Or like
we're going to look at how we get those poles today, and it does have to do with the moving electrical charges. I will say this, this unit could be extremely complicated if we were to go into a lot of detail about that question. We're going to touch on it, but magnetism, when we talk about it, is basically quantum mechanics on a macro scale, and so it's this really complicated stuff, but on a more real world scale instead of on the tiny scale. But the actual causes of it are pretty complicated. So I did put a link in the thing yesterday about reading about magnetic spin and stuff like that, because it is related to that. So if you looked at it, you might have some idea. If not, like I said, we're going to talk about it, but we're not going to go super in depth into it.
And if it's moving electric charges, how does it not lose its charge if it touches another conductor?
Let me go over the notes today, and then we'll see if you still have questions at the end. All right. Y'all have good questions, though, for a Friday morning. All right. So let's start with some definitions. I've got 4 of them up here, and you may already have some of this stuff written down, depending on what you wrote down during the simulations yesterday. But we have magnet, ferromagnetic material, compass, and magnetic field lines. A magnet is a material or object that produces a magnetic force. So if you have an object that exerts a force on another object due to its magnetism, then we would call that a magnet. A ferromagnetic material is any material that is capable of permanent magnetism, and our permanent magnets are made up of 3 elements. Okay, one or a combination of them if it's an alloy, but those 3 elements are iron, cobalt, and nickel. And so that's what we're going to see in a permanent magnet. If you go home and you have a magnet on your refrigerator, okay, and you pull it off, that magnet is probably made of iron. Okay, but it could technically be cobalt or nickel, but it's probably iron or some alloy of iron. Compass is an instrument which is used to find the direction of a magnetic field. You used a compass in the RA in the last unit, so you've already seen a little bit of the fact that moving electrical charges in the wire of your circuit was able to cause a magnetic force that affected that compass. Okay, magnetic field lines are a visual tool used to represent magnetic fields. They describe the direction of magnetic force. You have previously seen electric field lines. Magnetic field lines are pretty similar. They are a representation that we use to describe the force that would be experienced by a magnetic object or an object that could be attracted to a magnet, okay, within a field or the area around that magnetic object. So again, we've looked at field diagrams before, specifically with electric fields. They're going to look pretty similar, except now we're going to be applying the same kind of representation to a different type of force, but the field lines themselves will look pretty similar, and the rules are going to sound familiar. That's actually what makes this unit a little bit easier, is that a lot of the stuff we're going to talk about, you're going to see parallels with things that we have already discussed. By the way, if I go too fast and you're still trying to write, you can open these slides up on your own screen. I am currently on slide 4. Okay, so the how do magnets work question, and this may also get to the root of the question you were asking. I have a video clip that I'm going to show you from Minute Physics that goes into some of this stuff, and then we're going to talk about it a little bit afterward, but they have some good visual representations in here. So I'm going to show you this clip. I'm going to recommend that you give it your full attention because he goes into pretty good detail without being completely overwhelming and overcomplicated. But it's a good video. So we're going to watch this and then we will discuss it. So again, direct your attention up here, and if you want to jot down any notes while you watch it, please do so.
If you take a piece of wood and put it next to another piece of wood, nothing happens. And if you take a piece of granite and put it next to another rock, still nothing. But if you take this piece of iron and put it next to this other piece of iron, magnet. Magnetic objects are able to magically attract at long distances because they generate magnetic fields that extend invisibly out beyond the object. But the mystery is this: where do magnetic fields come from?
Well, that's easy, Henry. We've known for a long time that electricity and magnetism are really just two sides of the same coin. Kind of like mass and energy or time and space. They can be transformed into one another. And in fact, a magnetic field is just what an electric field becomes when an electrically charged object starts moving.
That makes sense for explaining why a current of electrons flowing through a wire causes this compass needle to move, or how currents in the Earth's outer core generate the geomagnetic field. But a bar magnet or the compass needle itself are just pieces of metal without any electrical current running through them.
Or are they? At the microscopic level, there are loads of electrons whizzing around the atoms and molecules that make up any solid.
Right. This brings up an excellent point. The magnetic behavior of any everyday object is influenced by a fascinating combination of effects ranging from the level of particles to atoms, collections of atoms, and collections of atoms. First, individual particles. Unlike the everyday workings of gravity and electricity, permanent magnets can only be fully understood as a quantum mechanical effect, in much the same way that particles like electrons and quarks have fundamental properties called mass and electrical charge. Most particles also have another intrinsic property called tiny magnet. Just kidding, it's called intrinsic magnetic moment. But really, that's just technical mumbo-jumbo saying that particles with electric charge also happen to be tiny magnets.
If you want to know why they're tiny magnets, well, you may as well ask, why are particles charged in the first place? Or why do objects with mass and energy attract each other gravitationally? No one knows. We just know that's the way the universe works.
Exactly, and since the 1920s, we've known that each individual electron or proton is basically a tiny magnet, which brings us to the level of atoms. An atom is a bunch of positively charged protons with a bunch of negatively charged electrons whizzing around them. The proton tiny magnets are about 1,000 times weaker than the electron ones, so the nucleus of the atom has almost no effect on the magnetism of the atom as a whole.
And you might think that since many, though not all, of the electrons are also moving, that like a current in a wire, they should generate magnetic fields due to that motion. And indeed they do. These are called orbital magnetic fields.
Except these don't usually contribute to the magnetic field of an atom. Here's why. Electrons in atoms are accurately and complicatedly described by quantum mechanics, but the gist of the story is that electrons congregate in shells around the nucleus. The electrons in any filled shell zoom equally in all directions, so the currents they generate cancel out and generate no magnetic field. These electrons also come in pairs whose tiny magnets point in opposite directions and also cancel. However, in a half-filled shell, all of the electrons are unpaired, and their tiny magnets point in the same direction and add up, meaning that it's the intrinsic magnetism of the electrons in the outer shell that gives an atom the majority of its magnetic field. So atoms near the side of any of the major blocks of the periodic table, which have full or nearly full outer electron shells, aren't magnetic, and atoms in the middle of the blocks have half-full outer electron shells and are magnetic. For example, nickel, cobalt, iron, manganese, chromium, etc.
Wait, but chromium isn't magnetic.
But just because an atom is magnetic doesn't mean that a material made up of lots of that atom will be magnetic, which brings us to the level of crystals. When a bunch of magnetic atoms get together to make a solid, they generally have two options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom, but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or, in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
If all of these domains are of a similar size, then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms within it.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist. I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable is that magnetism is a fundamentally quantum property amplified to the size of everyday objects. Every permanent magnet is a reminder that quantum mechanics underlies our universe. In order for an everyday object to be magnetic, though, it has to have a unified kingdom of magnetic domains, each made up of bajillions of magnetic atoms which also need to be aligned with each other, each of which can only be magnetic in the first place if it has an approximately half-filled outer shell of electrons, so their intrinsic magnetic fields can align and not cancel each other out. Not surprisingly, these criteria are pretty difficult to fulfill, which is why there are only a limited number of suitable materials you can use when you're building a magnet.
Or you could just run a current through any electrical conductor and produce a magnetic field that way.
But hey, why does that work in the first place? Click here to go over to Veritasium and we'll find out what special relativity and the speed of light have to do with electromagnets. I want to find out.
You're welcome to watch the Veritasium video on your own. We're not going to watch that one. But I did want to go over this because, as I said, it does explain the magnetism. But as I mentioned earlier, it is actually a really complicated concept. We don't go into a lot of detail in this class because we haven't learned all of the background stuff that you would need. But if we think about what we just heard in there, the basic source for all magnetism, which was also part of your warm-up, ultimately it's electrons. It's moving electrons specifically, but moving electrical charges. And all atoms aren't magnetic, as they said in the video, because not all atoms have electrons that can align in their domains. And again, that was just one of those levels. There were a lot of criteria before you got there, but it's the electron spin for the valence shell that determines magnetism. So metals with half-filled orbitals are best, and that assumes, of course, that the individual electrons also align in the same direction. And as he said in the video, that only happens with, or as we talked about, that only happens with, we're only going to talk about iron, cobalt, and nickel, but those three. He mentioned a fourth one, but we're going to stick with the three.
What is, I don't understand the domain part.
Give me a second, we're going to go over it more. Okay, so in case you weren't remembering what spin is referring to, I wanted to put this up here. Okay, because when we talk about electron spin, this is what they're talking about. You should remember having done orbital filling diagrams in chemistry where you represented each electron with an arrow that was either pointed up or down to represent either a clockwise or counterclockwise spin of that electron in that specific orbital. So these are the electrons, and in this particular metal, this is copper, there's only one half-filled orbital. So again, if you think of each of these electrons as a tiny magnet, like he talked about in the video, when you have one that's spinning clockwise and one that's spinning counterclockwise, they're canceling each other out. Okay, and so that's why he said that the ones with half-filled orbitals are best, because they're not canceling each other out there. But this is what it's referring to when it talks about spin. This is the representation that you used in your chemistry class. Okay, and so again, moving charges like electrons orbiting a nucleus will generate a magnetic field, and when you have regions of electrons spinning in the same direction, you have a magnet. Just as a side note, although we call it a spin, they're not actually spinning. Again, a lot of things that we use are simplifications, but we're still going to talk about it that way. But here's why you have magnetism with iron, cobalt, and nickel, because you have these electrons that are not paired up, so they're not being canceled out. And then beyond that, the electrons as groups are also able to align themselves in the same direction. So it takes multiple levels there, but that's why you're going to have things like copper and zinc that are not magnetic, whereas these objects are very magnetic atoms, and the groups of those atoms can form magnetic materials because they do happen to align in their domains. So again, there's multiple levels to that discussion. Here's that magnetic spin, again, being represented. This is typically how you see it. Again, it's a simplification. They're not actually spinning, but we're just going to go with it. And you can see that the opposite spin of these two electrons produces poles that are opposite as well, and these would cancel out within that orbital of the atom. Y'all remember this from chemistry, right? Okay. All right, so again, typically the spins cancel each other out, up cancels down, but when you have unpaired electrons like in iron, cobalt, and nickel, those spins can align, and if they all align in the same direction, you have a magnet. And we already looked at this, but there's those unpaired ones right there. Okay, so this is how we're representing domains. It's pretty similar to what you saw in the video clip that we just watched. So in terms of like what we're going to ask, like on a quiz or on a test, it looks like this. Which of these is magnetic? Again, it's not a tricky question, although the concept is very tricky. Which one of these would you tell me is the magnet, A or B? Yeah, B. I told you. It's not super difficult there to choose between the two. These represent the domains, and these arrows that are all, at least in B, are all pointing in the same direction, mean that there are groups of atoms that were magnetic in the first place with unpaired electrons that now those atoms have also aligned to give it this magnetism that you see here with everything aligned in the same direction. Okay, so B would be your magnet. All right, so again, so that's what makes something magnetic, is the alignment of the magnetic fields of the atoms that make up the material, and the fact that those atoms are magnetic in the first place because they have unpaired electrons. So now we're going to talk about that magnetic field that is produced by these magnetic objects, because if you do have a magnet, you are going to have that magnet will exert forces on other magnetic objects in its vicinity, and we can represent those forces with field lines. So the magnetic field is a representation of magnetic forces in a region. Magnetic field lines describe how magnetic force is distributed in the space around and within something magnetic with direction. Magnetic field lines always point from north to south when drawn around a magnet. You will need to know that, okay? So when we draw those field lines in the space around a magnet, they will always point from the north pole of the magnet to the south pole of the magnet. You'll see that over and over again, but definitely write that down. Okay, so here is an example of that. Like I said, from north to south, if you follow these field lines and look at the arrowheads on them, you can see that they're forming these loops. Some of them go off the top of my screen or off the bottom of my screen, but they form these closed loops from north to south around that magnet, which is what we just said. So magnetic field lines always point from the north pole to the south pole of a magnet, and those magnetic fields, just like electric fields, we've already talked about this before, but those magnetic fields will be stronger when the field lines are closer together. So again, you'll see questions like, which of these points, A, B, or C, represents the strongest magnetic field? And you would answer it in the same way that you did when we looked at electric field lines. If you have a more dense field at that location, you will have a stronger field there. Whereas if your field lines are farther apart, the field will be weaker. So if I were to answer that question, where is my field the strongest, A, B, or C, what would you guys say?
B.
B. Yeah, that's where our field lines are closest together. Good job, Edward. Okay, so B is where you would have the strongest magnetic field. And again, you just look at the field line diagram and you analyze it in pretty much the same way we already did for electric fields. Again, they represent different forces, but reading the diagram is the same. So when we look at magnetic field lines, again, these rules should also sound familiar. Your field lines never cross. That was true for the electric fields as well. Magnetic field lines naturally bunch together in regions where the field is strongest. That means the density of the field indicates the strength. Again, you've seen that before. And magnetic field lines don't start or stop anywhere. They always make closed loops. And so you will have these loops. It doesn't like just end. It will make a closed loop back from north to south. It just gets a lot weaker as you get farther away. You can actually continue drawing the field line inside of the magnet itself. Now, if you're looking at the way that it affects other objects, those other objects obviously aren't going to go through your magnet, but the field does still exist within the magnet. So it is actually a closed loop. Did you have a question?
Yeah.
Yeah.
In the lines, there's like different lines. In the little space between those lines, is there no magnetic field there? Like there's no...
There is still a force exerted in the space between the lines. He asked if there was still force in the space between the lines in the diagram. Yes, there is. It's just that it's the distance that the lines are spread apart represents the force in that whole area. That's the only way that they can represent it. So it's just a representation. Yes, those forces, it's not like they don't exist where there's not a physical line drawn. It's just a way that we represent the forces.
Can temperature change the strength of the magnet? Like if it's hotter or colder? Or is it all the same?
Certain types, yes. Okay, so drawing magnetic field lines, we show the direction of the field by drawing arrowheads along the lines. Sometimes those arrowheads are not drawn and the direction must be indicated in some other way. So again, if you see a diagram without the arrowheads drawn, you would know which way they were pointing anyway because you should know they're from north to south. So the magnet would have to have those poles labeled. And again, you would also know whether the poles were opposite poles or like poles based on whether or not that magnetic field diagram showed attraction or repulsion between two poles. So again, here is another type of question that you could be asked. I have a bar magnet here with the north and south pole labeled, and I could ask you to fill in the compass needle direction for each of these. So again, if I wanted to do that, your field lines are always going to point from north to south. And so they would look something like this. And so the compass is going to read the direction of that field line. So you can imagine placing a compass at any of these points and look at the direction of the field at that point. So for example, over here at this left-hand end of my magnet, my compass would be pointing this way because my compass points in the direction of my field. And so I would draw my compass needle pointing pretty much due left. Okay, if I looked here, I would have that loop that starts to go around. And so I would see something kind of at a diagonal representing one of these loops that you see here around my magnet. Okay, here again it's going to bend because it's a loop and it's going to start to go back this way. So again, you might see that there. If it was right next to the middle of the magnet or along the side of your magnet, again, because they go from north to south, you'd see them pointing to the right. And then they're going to curve back in over here to point toward that south pole. So they may look something like this. Again, I could ask for you to draw a compass at any position around a magnet, and you should be able to determine which way it would point by simply imagining or even sketching out those magnetic field lines. And again, the field lines look something like this up here. So again, I told you could tell if you have attraction or repulsion, and the shape looks pretty similar to what we saw previously with our electric field. So again, this should look familiar to you. So which of these shows attraction, the image on the left or the image on the right? Yeah, you can say it louder, Kimberly. Yeah, left. Okay, the image on the left. Here's attraction again. Opposites attract. It's the same rule as before. And you can see that indicated as well by the field lines that look like they're pulling the north pole toward this south pole. So this is attraction, this is repulsion. The shape also looks pretty similar to what we saw with those point charges and our electric field lines. All right, the Earth itself has a magnetic field. We're pretty aware of that. That's why we're able to use compasses to navigate, if you've ever done that. But the Earth itself is basically a giant magnet. Its magnetic field arises from moving iron in its core. Again, we said that it comes from flowing electrical charges. Well, the Earth's outer core is molten iron. And so as the Earth is turning, it causes the movement of that molten iron in the outer core, and that movement generates our magnetic field. Just as a side note, the North Pole on Earth, where you think of the North Pole geographically as being, is actually Earth's magnetic south pole. Okay, the north end of a compass points there because north and south attract each other. That's why we call it the North Pole, because the north end of the compass points toward it. But it is actually a magnetic south pole, so everything is just backwards from what you might have thought. You might want to make a note of that. You'll probably see it again. But again, the poles on Earth are flipped. Earth's magnetic south pole is its geographic north pole. And of course, the opposite would also be true. Our geographic south pole is our geomagnetic north pole. And again, here's what I was talking about. The compass, north end of that compass needle will point toward the south pole of a magnet, including Earth's south pole, magnetic south pole, which is at the North Pole. In case you want to make a note of it, typically with magnets, north is represented as red. So if you see a magnet like this, the red part's the North Pole, or if you see a compass, the red part of the needle is the North Pole. And south is usually represented as white or blue. So if you want to make a note in case you see a picture like this, that way you can tell what you're looking at. All right, so we know that magnets have magnetic fields, but so do all moving charges. As you saw in that magnetism simulation assignment, moving electrical charges generate a magnetic field. We saw a current carrying wire deflected a compass. You also saw that in your RA. We just talked about convection of the molten iron in the Earth's outer liquid core, along with the Coriolis effect, results in Earth's magnetic field. We have all of this movement and churning of this molten material, and so that's moving charges as well. I think you had this video or one like it in your assignment showing that field around the wire, so I'll just show the clip again. It's going to show what you just looked at yesterday.
Ersted's surprise. Physics legend has it that a physics teacher was teaching away, happened to have some stuff laying out on his desk, as like we all do, and when he hooked up some DC current electricity, compasses started rearranging themselves. This was the discovery that led to electromagnetism. Here I have a setup here of a little scooter battery and just a wire coming straight up with compasses around. Now, right now the compasses are all pointing north. What I'm going to do is, I'm going to connect this wire here, which then will cause current to go straight down and then back through this wire back to the battery. Now, if current is going down, we expect the magnetic field to go in a circle like this. So all the compasses should rearrange themselves so that they're in a circle like this. And let's see if that happens.
So again, you can see the same thing.
You can see the compasses show the magnetic field lines, and the magnetic field lines are in circles around the wire.
Similar to what you saw in the RA with the deflection of the compass, but this time you're looking at it all the way around, but it does form a circle around the wire. You also saw that in the simulation yesterday. In fact, it looked like this. And so you could also represent the compass needle at the different positions around it, and it does change, and it does point in a circle around a wire. So just like a permanent magnet, a bar magnet, current moving through a wire also creates a magnetic field. You do need to think three-dimensionally when describing these fields because it is going in a circle around the wire. Yes, sir?
Can magnets create heat? So I feel like I've seen videos where like they put something in, like something that spins and it gets all red and hot. It's like floating. And
I'm not sure what specifically you're referring to, but if you can find it, we can look at it. All right, so again, we just talked about this. Moving electrical charges generate a magnetic field, so our current carrying wire, our molten outer core, both create fields, but what if the charges aren't moving? What if you just have a stationary charge? Static electrical charges still generate an electric field. We talked about it in the last unit. We looked at, or not last unit, but in electrostatics. We talked about electric charges that weren't moving. We did get an electric field from that, but we did not get a magnetic field from that. We only got magnetism occurring when the charges moved, like they did when they were flowing through the wire of our circuit. So just as a reminder, an electric field is a field of force surrounding a charged particle within which another charged particle experiences a force. We've talked about this already. I'm just reviewing it with you because these are both different types of field forces. And so you do need to be able to compare and contrast those field forces. So this is your electric force. We know that we have electrostatic attraction anytime we have oppositely charged objects or particles, like for example, a sodium ion and a chloride ion. You would get table salt from that sodium chloride because the positively charged sodium and the negatively charged chloride would attract one another, and you have electrostatic attraction that forms that ionic bond. Okay, or you could rub a balloon on your head and make your hair stand up, and they're going to attract each other for a similar reason, but on a little bit of a larger scale. So you can look at these static electric charges, and they do still exert a force on things around them. It's just that that is an electrostatic force as opposed to a magnetic one. Okay, but they are both types of field forces, and there are a lot of similarities there. You can build up an electrostatic charge on an object like a glass tube and use this to cause styrofoam pieces to jump to the tube, or we looked at balloons being charged up.
Now, if I take this glass and I rub it with oil on, I'm going to give it a charge. And watch what happens when I bring it near these small pieces of
So
gum.
it almost looks like it's magnetic because they just jump up to it, but this is not magnetism. This is electrostatic attraction. Okay, he's built up a charge on that glass, and that styrofoam's attracted to it. Again, they behave kind of similarly, so we do compare them because they are both field forces.
Which one's stronger?
Your electrostatic, yeah. Okay, the electrostatic force on an object is a result of charge imbalance between two objects. Again, remember opposites attract like repels. That's the same rule that we just looked at with magnets as well. Opposite poles attract like poles repel. Here it's opposite charges attract like charges repel. And again, we can represent these electrostatic forces by electric field lines. This is what our field lines looked like in that unit. And again, the shape is pretty similar to what we just saw with our magnetic field lines. One difference, though, is that you can never have this image that's all the way to the left with a magnet. There is no such thing as a magnetic monopole. You can't just have a north pole or just have a south pole. So you can't see this. Like this is just a single point charge with a magnet. A magnet will always have a north and a south. Okay, so it's a little bit different, but the field lines and the shapes that we see for attraction and repulsion look the same. All right, so these are both field forces. Again, a field force is also known as a non-contact force, and it's a force that acts between two objects that are not physically touching each other. So both that electric or electrostatic force and our magnetic force are field forces where you can see an attraction or a repulsion between two objects that are not actually in contact. But there's one other field force that we also talked about this year that you still need to remember as well, and that is the gravitational force. So we have three field forces that we talk about in this class. The gravitational force, again, as a reminder, is a field force that causes the attraction of any two objects that have mass in a gravitational field. The magnitude of force can be calculated using the universal law of gravitation. One difference about this one, though, gravitational forces are always attractive. Magnets can repel, like charges can repel, but gravitationally, objects can only be attracted. Okay, so again, like I said, you need to be able to compare and contrast your field forces. So hopefully you have made some notes about gravitational force and electric force as well. Here's your electric force. Again, it is a field force that causes attraction or repulsion between any charged particles in an electric field. If the charges are stationary, the force is calculated by Coulomb's law. If they're moving, then of course you also have a magnetic field. But here was Coulomb's law. That force of attraction or repulsion was calculated by this equation, K times Q1 times Q2 divided by the distance between them squared. We're not going to do the math again. We've already done it, but I'm just putting it up here as a reminder. Here is magnetic force. I did put the equation up here. However, we will not actually use this equation. We're not doing any math in this unit. If you want to do the math for magnetism, then I would suggest that you consider taking AP Physics 2. Because that is where they do electricity and magnetism. But magnetic force is a field force that causes an attraction or repulsion between any two magnetic objects or moving charged particles in a magnetic field. This can be calculated by the Lorentz force law, which you see up here. You do not need to write that equation down. All right, running a current, which of course means we have moving charges, through a wire in a magnetic field will produce a force on the wire. We just talked about the fact that there is this force that's exerted and that moving charges do create a field. And if we have that field around another magnet, because both of them are generating magnetic fields, you will get a force of attraction or repulsion. You're going to get some movement here. This is kind of cool. He runs a cable with current through these two horseshoe magnets. I will say he forgets to turn it on at the beginning of the video, but it's a cool demonstration.
This is a demonstration of the force on a current-carrying wire. Power stations need to bolt their high current wires down. And the reason is, if there are magnetic fields around and currents, those wires that are carrying the currents can experience large forces from the magnetic fields. What I have here is a battery, and what I'm going to do is touch this piece of copper to this piece of copper to complete the circuit. But the bottom line is, I will have a current in this red wire. It's just a jumper cable wire. A current that will be in this direction. And magnetic fields produced by these horseshoe magnets that are horizontally toward me. And so the current, put my thumb using the right hand rule.
You'll learn that
later. In the direction of the current in the wire. My fingers in the direction of the magnetic field of either one of these magnets, and the force on this wire will be directly
But if you
outward.
wanted to do it God's way, you'd be doing
What you'll be looking for, not only, I'll do it a couple of times so you can see the spark as these two things come together, because I've got essentially zero resistance in this circuit. I don't want it to run very long, I'll burn the wires up. But just spark a tiny jolt of electricity through that wire should be enough to pop it up.
He doesn't turn it on first, so he's about to realize that.
You know what? I'm going to turn on the battery, and that will help this work really well. So now the battery on.
So watch the wire. He's not touching it. That's just the magnetic force.
So a little bit of spark here where we complete the circuit, and then the amazing jumping wire. And that's the force on a current carrying wire.
So again, you can get this force, and he said they have to bolt them down because of that, because otherwise they're trying to jump off the ground or whatever. Okay, so there's a few questions in here as well that we can talk about, but you're going to see stuff kind of like this in your assignment today also. But if you have a picture like this where you have magnets levitating one above the other, this is going to happen if you have repulsion. And so if they label one pole, like up here, if I call this north and I know this is south, and I know that if these are floating like this, that they have to be repelling. So if this is south, which makes this north. And you can go through and figure out any unknown pole that I ask about based on its behavior and how it's attracting or repelling other poles. All right, guys, so for the rest of the class period today, which is about 10 minutes, you have the assignment it's actually 1202.1, Magnetism Basics Problem Set. So I'm going to encourage you to work on that. If you have questions, let me know. And on Monday, the assignment has 2 video clips. I'm not going to be here, so I'm not going to be able to show them whole group. So please bring some headphones so that you can watch those video clips without everybody's computer making sound at the same time. All right, guys, if you have any questions, please let me know.